Okay, kind of wondering if I'm working my little video capture thing properly, but right now I'll leave it as it is. We'll see how that goes. As I said in the last little video section, we got some stuff in here we don't need. Now I'm going to go ahead and unhide all the layers, as you see me doing right down here. Like I said, most of the stuff we don't need, and this makes your files grow big if you leave a bunch of garbage in there, so I usually clean out the files to begin with. Now this right here, move that up out of the way. We're not going to need this. Not going to need this or this. This I'm going to go ahead and put it on a not used layer. So I'll go ahead and hide that right now, because that may come in handy in the future for some reason. Go ahead and get rid of that. Not going to need this or this or this or this cross section that I did, or this big box, or this little hinge thing. A bunch of artifacts really left over from the previous project, and generate a lot of junk like this. This we won't need for this, so I'll go ahead and move that to that layer. I don't think we'll need whatever those are. Rid of all this. In fact, I'm going to go ahead and just select all curves. Let's see. I'll find out where to do that. Let's see, there it is. Let's lose it. Select all curves. I'm going to just delete everything. This is going to be a totally from scratch design. When I redesigned this, that's why I didn't want to make a video of it, because I kind of referenced the other project, but I figured you guys might be more interested in seeing a totally from scratch design on this, with the exception of some of the parts we'll reuse. I'll go ahead and leave the circuit board right now. We're going to have a roughly circular circuit board. Now this I can actually reuse. I'm going to go do a 2D scale on it. Actually, 2D scale on it. Click it there, and I'll pull it out to about there. So that actually gets that size, and I can go ahead and move this sucker. Oh man, let me put my... You push tab in Rhino, it makes a constraint, so no matter, what they call an elevator. So, if I don't have that on, I can pull it out this way, and anytime I push tab and that line turns white, it'll constrain it along that direction. So, if you see the line turn white, that's what I'm doing, is pushing tab. Give it an elevator constraint. Okay, we got that. Now this resistor here, I left that on these layers. We might need some, as we look at this, see, this is an 8 watt resistor, and I believe these are half watt, I think. Because I drew an 8 and a half and a quarter watt, but I don't see a quarter watt in here anywhere. I may end up needing them for this, I'm not sure. Here's one of our switches in default position, but that's no big deal. I'm going to go ahead and just turn this layer off then. We'll just leave everything that's there. And like I said, on this video too, I'll take you through all the steps, including the circuit board part. Although the circuit board part I may actually make publicly available. But I am using these particular LEDs. With this project, you can see they do have standoffs on them. So, you know, I'm taking that into account. That's why I'm, you know, wanted to keep some of these parts as they are. Like I said, I'm not sure what I'm going to do with this thing just yet, so I'm going to go ahead and kind of scoot that out of the way, and with that I want to grab all this and scoot it up out of the way above our battery stack here. Then I go ahead and move this. I'm going to select my between 2 points and put it right there, so that gets us, you know, right here. That's pretty much on the working plane. That's what that red is. That red line is our working plane. You know, that's this plane here, and this green line is one of our working planes, which is this view here. So, and you know, you can see two of these lines coming right here. Anyway, the point is that that's got us basically set up, you know, to start actually doing something. And that's why, you know, too, remember when I had the calipers and I measured this tube here, you know, I wanted to make sure the wall thickness is fairly accurate and so forth with it, because, you know, this tube is actually going to scoot around a housing. So because I want this housing to periscope up, and when I actually do the video edit, you know, you'll see what the end result's going to be before I start you know, going into the video, so you kind of know what I'm doing with this, because even I don't know right now. But you know, I'll show you the finished design, you know, at the beginning of the video, so you see what we're aiming for here. But you'll see that this part here is actually going to go around a smaller diameter tube, and of course I'll leave some definite tolerance in there for that, you know, some wiggle room. But this thing's basically going to, you know, be able to raise up. Let me put the constraint on here. It's actually going to be able to, you know, be retracted, but then raise up and twist and lock in, so it becomes a diffuser, you know, to scatter light, you know, off the top of it. When it's down, the LEDs will actually poke through it. You know, in other words, just paying attention to this area here, you know, if this was up and you had your diffuser on top of it, you know, the light would hit that diffuser and backscatter, and since it's translucent, it would also forward scatter through it. But then you can actually lower it around the LEDs and the diffuser will poke through it. Let me show you this way, because this includes the diffuser. So it's in a raised position, you know, light will scatter off of that, you know, that diffuser you see here, so it'll scatter off of it. But then when I lower it, you know, it's in flashlight mode, so the LEDs will poke through it like that, and they won't be the light won't scatter. So anyway, that's kind of the objective, you know. That's I'm trying to outline to you at this stage in the game what I'm kind of generally trying to achieve. You know, that's one of the parameters. The other parameter I'm considering is that it's got to accommodate this double stack battery, because with 8 of these batteries in here, that'll give us 12 volts. Okay, now 12 volts is great because I can actually drive 3 of these LEDs in a series chain. These LEDs have approximately, they're white LEDs, so they have approximately 3 volts drop across them. So that 3 plus 3 plus 3 is 9 volts, but it's actually sometimes a little over 9 volts and sometimes a little under. You never know, so you got to leave you some headroom in your ballast, so that's why we got the extra 3 volts above that 9 volts. The total 12 volts will drop that across our resistors. That'll also help extend the life of this thing, which is one of the reasons I'm doing it this way. You always want to leave some headroom in it. Because you may be thinking to yourself, well, if it's 3 volts, you know, I can put 4 LEDs in it. Yeah, but you're going to have no control over what current goes through it, or whether you can even get the maximum current remains to be seen. Because the fact of the matter is that every LED, you know, that's ever been manufactured, even if it's from the same production batch, the same part number, everything, you go through and measure the actual parameters of each and every LED in a bag, and hell, just measure 10 of them. You're going to find that the forward voltage drop across every LED is different. So, some of them might be 2.8 volts, some of them may be 3.5 volts, etc. for the same exact current. So the point is that you got to leave yourself leeway, and you got to leave yourself ballast room on things like this. The only time you can get away from that is if you want to get extra complex and put a constant current source in it, which honestly is just overkill. And it's just with LED technology, and there are many other technologies that this is what true for as well. With LED technology, generally speaking, keep it simple, stupid. The simpler the better, then the more reliability you're going to get. The more complex you make your circuitry, the more points of failure there are in that circuitry. So I tend to design very simple LED products when I get, the opportunity. Whenever I can. Bear with me for a minute, I'll be back. Okay, I'm back. I had to turn off the oven timer thing. But yeah, there are, like I said, when it comes to LED products, though, the simpler, the better. And, my technology's proven that out. The last 20 years, I have nearly 500,000 feet of LED product, LED lighting I produced, all over the country, and I guarantee you, if you're listening to this tape now, you have seen my stuff in action somewhere. At some point in your life, you have seen my product at work. But the fact of the matter is that keeping it simple, just means fewer points of failure. A lot of people I see come up with LED flashlights. I see them on TV all the time. I don't know what the heck is wrong with them, but they want to go and put, PWM circuitry in it and everything else. They make it unnecessarily complicated. And there are times, and again, I may even come up with a version of that myself, because, you get infinite variability. Well, not infinite, but, you get a large range of variability and so forth off of it. But at the same time, you're making something that's more complex. And this device I'm designing here is not, for aesthetics. It's not, for, casual use. It's for an emergency. And I would like things to be as reliable as possible. In fact, if I had my way about it, I wouldn't use these stupid switches. Originally, I was going to base this off of a magnetic reed relay switch because it's sealed, and use magnets. Had a pretty clever little design, for using reed relays and magnets, which would be totally sealed switches. And I also got a great idea, too, of how to make a reliable battery holder as well, which I'm going to get a patent on since nobody's done it. Because, one thing, everybody, has experience with, even with the newest flashlights out there, these LED flashlights, you shake them and they start, the lights start going off and on, because the battery, contacts suck. Well, with a bunch of springs and stuff, you're never, unless you're going to make everything out of gold and titanium, you're never going to get good reliability out of those, standard battery holders, and you pay a fortune for it. Well, I've got some ideas, but again, I can't incorporate these into this. I'm still designing these products as if I were going to put them out on Kickstarter, and I got to keep it in perspective about what people are going to be willing to pay for these things, and what they're going to be able to afford, etc. And these switches, happen to be inexpensive enough and still reliable enough to where they should work okay because of how the circuit is designed on these things. It should give you some reasonable reliability, for it being an emergency candle. But again, it's not as good as I could do. But again, it's a question of what the market will bear price-wise. And that's why even in the earliest stages of design, I always think about cost. I really practically never just prototype something without thinking at all about what the final cost is going to be. I always have some general idea, what my target is before I even start real design work. And that's the case here. I spent a lot of time trying to find these particular switches, and they're not the ones I'd like to find. You know, I really wanted a switch that, you know, really just has like, you know, 6 or 7 positions on it, but unless you're willing to order a bazillion of them or to have somebody build a custom switch for you, I just can't find any. So in any event, you'll spend a lot of time digging for parts, trying to find something that's along the price lines you're looking for and everything. Because I don't ever do designs until I have all the non-mutable parts accounted for. In other words, I always know what, by non-mutable part, I mean a part you can't change. I can't change the dimensions of the battery holder. I can't change the dimensions of the switch, etc., unless I want to have something custom made, which you'll spend a fortune doing that. It's certainly possible to go that route, but I'm no Fortune 500 company or anything, so that's not going to happen. So, and two, a lot of the design decisions I make too, even on these plastic parts, keep in mind I'm trying to aim for keeping the tooling cost down. Particularly that last one, even though that 9-volt LED candle that I just showed you, that's not a complete DFM design by any means. I mean, I actually need to design that in a different program to get it ready for plastics. But the fact of the matter is, even though I could do it in Rhino, it's just an extra pain in the behind. So I'll probably do that in Solid Edge or something. But but in any event, I generally try to design the parts thinking about injection molding and trying to keep the tooling costs down. But this is going to be a great example of a device that if I were to have this injection molded, the design I'm going to do on this, the design I kind of have in mind that I'm going to do on this, would probably cost a heck of a lot because it ended up being a very complicated mold, for the injection molding tooling guys to build up. And that means, it's going to cost you a lot more. So I don't know that I'd ever take this version to market, but again, I'm really just kind of doing this as a proof of concept, just to evaluate whether this is going to be a workable idea or not, and basically to put in my, my video set to sell to telebrands, because that's why I'd like to have 2 or 3 different versions of each of these two baseline products that I'm doing here. To put in my telebrands video, because they may be more interested in one than the other, even though I think that 9-volt model is going to be the king and my tack light model is going to be the base model is going to be king, but I've still did a couple of versions of that too, just to have in my video, because again, it's good to give people some variety, and when they know, if I'm trying to license the patent to them, or actually sell them the patent for $1 and get a royalty out of it, really all those product varieties, and including any embodiment I have in the patent, the PPA, the provisional patent that I'm going to do, would be included in it. That's the theory. Make people feel like they're getting more for their money. There's always been a philosophy of mine when it comes to business. So, and certainly offering people choices is a good way to, go about that. But in any event, this just gets this thing set up. So I mean, I've gone through and cleaned up the drawing and gotten things basically where we want them, and I showed you kind of what I'm going to do. But I know this battery here, what I'm going to do is I'm going to make the bottom half of it like a cup, and with probably an extended flared out base, so it doesn't tip over so easy. And then I'm going to make probably a thread down the middle of it, right through here or so, where the top half actually screws onto the bottom half. So that's how you change the batteries, basically. So anyway, but that would be a very expensive thing, I'd imagine, to to have injection molded, because it's very difficult to injection mold a part that doesn't just cleanly come out. That's why normally, when you're injection molding a part, let me show you just a little simple idea here. Normally you want to have a taper on a mold. So let's say you know, that this is what we were making, is some kind of a cup here. Now, if they're going to make a mold, well, let me see if I can shrink this down a little bit. I grabbed the wrong one, but still get the point. Okay, let's say, you know, this is like a cross section. You know, this is the top half of the mold right here, and this is the bottom half of the mold. Because this is tapered, you know, they'll have a sprue, what they call a sprue, which is where the hot plastic comes in, and that'll tap in. Like, for example, if they had a sprue that connects to their injection molding machine, and the hot molten plastic will pour through that sprue and come in here and fill up this volume in here. And let's just think of this as a drinking glass, you know, a plastic cup. So, and this is just a cross section through the tooling mold. Well, the point is that, you know, once the injection, or the plastic is injected in there and it sets, then the mold halves separate, and then a little pin, you know, pin mechanism is down here, which tends to thump the bottom of the plastic cut, causing it to pop out. Well, that works great, you know, as long as you have a taper. Now, if you didn't have a taper, though, the problem is that different types of plastics do different things. Some plastics expand, you know, when they're hot, like you'd expect, and contract when they're cool, and they'd pop right out of a mold like this, or even if the mold were straight walled. But the thing about it is, you know, is that if this were a straight walled mold, you know, if this were a straight walled mold, kind of like this, and it had an insert in it, like this, you know, where the two, well, you know, if the two halves are like that, you know, well, that's fine and dandy, but you pour the plastic in there, but as it starts to cool, and let's say the plastic shrinks, well, when they pull this half of the mold off, you know, so they can eject the part, well, what happens is your plastic part's actually still stuck around this mandrel, and that can be hard to get off there, and you know, hard to eject it, and it'll be, you know, could be pretty tightly wrapped on there. And if the plastic happens to expand when it cools, which I'm sure there are some plastics that do, you know, then they couldn't get it out of here. It would be stuck in here because it's straight. You know, but if you have a flare, you know, a taper on the sides of the mold, well, it's a lot easier to get the parts out. So you do have to put a taper. Now, I'm not sure what the parameters are. They kind of will vary depending upon the manufacturer, but, you know, it's possible, you know, to make a mold that does a straight object like this, but the tooling is not going to be simple. See, this would be a very simple mold down here, but this, you know, they may have to have some kind of mechanical device here that either is able to push this piece off that's swollen onto this, or to actually shrink that internal part in some way. In other words, it may have to be a pretty complex mechanical mold in order to get the actual part to fall off of it. So that means more expensive tooling, if they can even do that. You know, just it depends on a lot of parameters. But for something like this, you know, you can make this as deep as you want, you know, because it's got a taper to it. So it's always going to be very possible to get the part off the mold, and that means cheaper tooling than something like this, which would mean more expensive tooling because it's just totally straight. There's no taper in it whatsoever. So that's one of the things you got to kind of watch out for when you're designing parts. And, you know, and again, I'm going to break that rule with this, you know, because I know it's possible. You know, you look at certain flashlights and so forth, there's no noticeable taper on them. you know, on some plastic flashlights and so forth, and other plastic parts I've seen. But you know, it's just hard to say how they actually manufactured it. And this, you know, given the fact I still have not done too complex of injection molded parts, I still don't know what all the manufacturer's constraints are. But I can at least reason out some of them, and this is one of them. You know, I know this will be cheaper tooling than this will be. You know, especially if that's, you know, very complex. So, you know, another thing too, you know, is that, you know, you can have parts, like for example, let me draw you something up real quick. Something real quick and dirty just to teach you a little bit about this. Let's zoom over here. Okay, let me, you know, make a part like this, and let me put a little extension here, and then a little, oops, and a little like a hook here. You know, which you might have something like this as part of a latch in a battery compartment or something. So let's say you wanted to have a part kind of like this made, you know, for like a battery, you know, compartment lid or something like that. Well, the thing is that since you've got this little thing latching over here, this would actually be a difficult to injection mold, because, you know, you can think about the various ways they could produce it. This one they actually could do simpler than others, because they could actually make it, you know, they could actually make it sideways. So, you know, you can think of it being on end, and, you know, with right here would be the bottom half of the mold, here's the top half of the mold. But still, that's difficult tooling just from a machining standpoint, particularly if this were a very thin part. That's very difficult tooling to try to make, to try to carve out a cavity like that. It would end up being some pretty complex tooling, even if they did make it sideways. So, you know, the point is, though, is that if this thing, let me pull this out of our work zone here, but let's say this thing also had, well, let's say it had a shape more like this, for some reason. Extrude that out. Okay, and get rid of this. Okay, so let's say that right here, this is the shape we wanted. Well, hell, that's not really what I wanted. Okay, let's say that's the shape we wanted, and let me change the orientation on this. Well, actually, let me just copy it. Now let me mirror it. Okay, now let's say this was the part they wanted to make. You wanted to make here. Now, like I said, that precludes us having a mold that is vertical. In other words, this can't be the bottom half, that can't be the top half, because it's got these little latches on it. You know, so that's sort of a problem. But anyway, it's got these little latches on it, so that's, you know, sort of a problem. So again, to make something like this, you know, there's no way of actually pulling it out of a mold, you know, any which way you want to make it. So the point is it has to have some pretty complex mechanical apparatus in there to when the plastic, after the plastic's been injected in there, that these little parts, you know, mechanically release and so forth, you know, so that the part can be ejected. Well, the point is that gets to be pretty expensive, when you start dealing with tooling like that. Again, the more elaborate it's going to be, the more expensive the part gets. I mean, having a simple part, like just this lid alone with no, even this would be pretty expensive. But just having, just a simple injection molded part, like let's say we wanted to do this disc up here, that, with a couple of holes in it or whatever, would be a pretty cheap part to tool by comparison. It might just be, again, I haven't checked on tooling for quite a while, but it might just be a few $1,000s to have a mold made for that. Whereas this one, hell, this may be 50 grand. What the hell's going on here? This may be 50 grand having this one made, just because the tooling is so elaborate. Again, the more complex your part, the more the tooling is going to cost you. And I try to keep tooling down because that's still a big deal, especially if we end up taking this to Kickstarter. However, if Telebrands or somebody like that goes for this product here, they might not care about that because they're going to have to redesign it for their, have their factories redesign this for manufacturability in their plant anyway. So it really doesn't matter how I design it. What they're going to be interested in is just the fact that here's the idea, and here's how it works. So I don't have to worry as much about that with some of these, about the DFM, because I'm not necessarily going to take this to market. But like the LED candle, the 9-volt one, if the Telebrands project fails, well, I might put that on Kickstarter or something and try it out there. Same with the tack light. That's why I'm spending a little more time trying to get those a little DFM-ish anyway, even though I'm still going to have to redesign them later, but I can still evaluate the actual design here in as mature of a way as I can. I'm trying to get it at least close to the form and appearance, of an actual DFM part at this point in time, but without actually going through the complication of trying to do an actual, 3D part. Because like I said, that LED candle that I showed you earlier, the one with the 9-volt battery in it, that's for the 9-volt battery, would be very difficult to 3D print. That's kind of the problem. I'm just kind of looking at. I'm going to have to rethink that the way I do that to actually 3D print it. And I can 3D print it if I do it in pieces and kind of glue all the pieces together. But that's what I'd have to do. And right now I'm just trying to evaluate the final form of it instead of how it would intimately be built mechanically. So it's the same for this. This is just to give you an idea. But this really wouldn't be the best way to go about it if you're going to actually go into production with this thing. You're going to want to make some DFM decisions about the manufacturability of it and what that's going to cost you and setup and production. Because it's better, when you're actually doing a part, to try to keep, when you're just going into business, to try to keep your tooling and setup costs as low as possible. It may not be an ideal version of the product you might be going to market with, but to go to market with one you can afford to go to market with. And then if it succeeds, do it as good as you can. But if it succeeds out of the market, then later on when you got money rolling in, then you can actually re-engineer the thing to the way you'd like to have had done it the first place, to begin with, but couldn't afford to do. So it helps you keep your startup costs down. And that's what you want to exercise when you're doing things like this, to try, to go about it in such a way where it's going to reduce your startup capital requirements, because that's going to be a big killer. You'd much rather have capital available for operations, the startup operations, as opposed to, actually having to invest it in parts and so forth, and tooling cost, things that have to generally be amortized. It's nice to actually have that a capital as much as you can. If you got a given batch of money together, the more of it you can use for startup, advertising, basically launch capital and your initial operating capital, the better. And the less you have to spend on parts tooling, the better. So it's good to try to mitigate that, and it's just thinking some things through and looking at things a little differently than you may be with whatever product it is you may have in your mind, to try to make them efficient to manufacture, not just for you, but for your suppliers. That could actually save, translate into savings in you know, some of your startup cost. So, you know, even though, like I said, there's a lot of things they can do, they may not tell you, hey, there's a, you know, if you make a couple of changes here and there, you could actually have cheaper tooling. You know, your plastics companies probably aren't likely to tell you that. You know, they just know you're giving them a part, they don't know what your intent is, and they just will tell you if they can make it or not, and how much it'll cost you, and how much the tooling will be. So, you know, how much production runs will cost you, and how much the tooling will be, and what your unit cost and your tooling will be. So, you know, that's what you're kind of looking at. You know, is you know, again, doing what you can to reduce those NRE fees, those non-repetitive engineering fees, the tooling costs, to get you started. And then after that, when the money rolls in, you know, then you can, you know, do whatever you can afford to do, you know, down the road. But, you know, you want to get a product out there, of course, that will succeed on the market. You know, you can't compromise too much, but on the other hand, you should try to compromise as much as you can, you know, within reason, just to keep your launch capital as low as possible, particularly if you're doing something like Kickstarter. I mean, you know, because you don't want to, you know, have to set your funding goals so high, you know, on a Kickstarter campaign that you're going to spend all your backers, you know, that you're going to have to, you know, raise way too much money to where it'll never fund, because nobody wants to back a product that's, you know, not going to fund. You know, if you have to set your goals too loftily, they probably won't fund you. You know, so you'll probably be sitting there holding the bag. On the other hand, you know, you still got to make it, you know, pizzazzy enough, you know, to where they'll want to buy it. But that's why, you know, a lot of careful consideration has to go into your design, because but on the other hand, you know, you got to keep the cost realities in check, and realize that Kickstarter, if that's your goal, is not a bottomless well there. You're going to have a hard time with some products, you know, reaching your funding goal if you have to set it too high to begin with. So, you know, that's why I always aim for parts that might just cost, you know, $5,000 a piece in tooling, you know, but as much as possible. But at any rate, but like I said, it will be necessary to, you know, to keep some of these DFM rules in mind when you're designing whatever product you're going to design. And this is just very preliminary stuff, but I certainly suggest, you know, looking into the subject more in depth. You know, there are several design guides out there, you know, about what to do and what not to do, and, you know, in injection molded part design. I'm sure I'll have some links to some of those or whatnot, you know, and the final documentation on this. But you know, the key is a simple mold should translate to less costly tooling, because it translates into at least less machining time and less engineering time. Because, like I said, the design of these molds can be very, you know, very complicated. I mean, requiring an engineer. So the more time you eat up in machining and engineering time, the more the mold's going to cost you, outside of just the raw cost of the materials themselves. But in any event, you know, this is enough to kind of get, you know, started. We got a blank slate here, and we'll pick this up, you know, in the next section.